So the slide that I'm going to present here, they are adopted from the presentation that I gave at a ADBT conference back in 2018. And this is a work that I really spent most of my time while I was at IBM Research. All right, so kind of give you a little bit of background on this, because I think that's important as well too, to get, we talked about sort of the state of data management at scale. And I think kind of let's look at it also pictorially as well. So if you look at a single person, the data for that person is all over the place. They may have credit card transaction, they may have FICO score, they have IRS records, they may purchase stuff at Walmart, they have insurance. So individuals, a single entity has information all across these silos of databases. And so at this macro scale, we always find that there's an integration problem, and then there is a lack of coherency and be able to form an image of all the data of this individual. Of course, there's a lot of important privacy and ethical issues. Probably not, maybe not even a good idea to anyone to have access to a consolidated view of the data of a single user. Maybe the user, I think, is good to have that access, but I don't think it's wise, or nor it's doesn't really make sense for any other entity to have that such a global access to user data. I think the privacy laws, I think, is important. As computer scientists, I think we need to really be sensitive in educating ourselves and educating others when it comes to privacy. But nevertheless, it is an important problem, is that how do I deal with these islands of information? How do I integrate them? How do I query them? How do I make sure they're consistent? And so it is a technical challenge. But the problem, it's even more challenging. And this is really perhaps comes the focus of this course, is that if you look within a single organization, let's look at Walmart, for example, what we find is that they have this really right optimized engine, their OLTP, online transactional processing, that are really good for sales, to process hundreds or thousands of transactions per second. So they want to be able to cope with Black Friday sales. So these systems need to be provisioned for that one night, because the amount of money that is being exchanged, the amount of sales being exchanged is going to happen that night. It is probably going to be a large portion of the entire year. So any second of downtime or any time that the customers turn it on, revenue is being lost perhaps by millions during those important times. So they develop these systems that are really right optimized and potentially role-based, because they talked about the importance or the benefits of having role-based. But again, as we talked about also, is that just doing sales as fast as you can, it's not going to let you to run an enterprise, but you also need to have OLAP, or online analytical processing. You need to be able to run reports. You need to be able to do forecasts. You need to figure out what the next set of items you're going to put on sale. Or you need to figure out if there is a fraud that is happening, or is there some sort of an attack that is happening. So these are all type of analysis that are, if not as important as our day-to-day transaction, then probably are more important, because without the right vision and the reporting and analysis, well, the future of the company or the future of that enterprise, it's probably would be unclear as well. But traditionally, again, we have solution and product that really focus on data warehousing solution, really optimized. And we've seen in the last 10 years or so that they tend to have that columnar layout or flavor. So on one side we have row, and the other side we have column. And again, major entity, major organization do spend and invest in these creating this product. For example, DB2 or IBM or Oracle, they have solutions that are OLTP optimized, and they also have solutions that OLAP optimized. And given the sort of the hype of the big data, something started in early 2000, 10 and so forth. And the big data is defined by the high volume, high velocity, and also the veracity and the variety of the data. The veracity is perhaps maybe the uncertainty, the variety, the different kind and form of data, whether it's XML, JSON, media, and so forth. Volume is just the size of the data. Velocity is how fast the data is, for example, changing. So how fast I can do transaction, that's a form of a velocity. But petabytes of data I need to analyze, that would be volume. So that kind of took turn, this big data, the notion of big data. Again, really around 2010, I think probably that was the maybe at the height of this in research. So if you look at the type of application and services and products are being developed and technologies in 2010, in 2012, there is just the field is just growing at an amazing rate, and they are finding niche solution for very niche kind of workload, not just, for example, just a general transaction, but maybe very specific kind of transaction, as opposed to be just general analytics. I'm just going to do analytics for graphs. I'm just going to do analytics for XML, or I'm just going to do analytics for a subset of graphs. So specializing in further specialization. And you see how many products we have in 2012. And as a customer, which one are you going to choose? And you probably have to choose one in each of those categories. And how are you going to integrate? How are you going to maintain? And it becomes, sure, there's a lot of creativity and innovation that is happening, that we have all these different solutions, but in terms of consumption is a challenge. 2017, a few years later, that's the state. I mean, again, it shows so much activity, so much sort of promise in this in the field, but as a customer, how are you even going to which one are you going to choose? And you may need to use a dozen of them. How are you going to deploy? How are you going to maintain? It becomes more and more. And after 2017, this thing gets bigger and bigger, but I think it just no longer fits in one slide. And I'm not sure the person who was Matt, who was maintaining this along with his colleague, I'm not even sure if they continued, because it just, maybe this already illustrates the growth, but also how unsustainable this ecosystem is going to be if you further try to specialize and specialize and specialize to do a small task faster and faster. So kind of coming back to the problem of analytics and transactions, so the point is, could I unify these two? Can I have a single engine that is both write and read optimized? And starting in mid 2010, not 2010, or probably around 2015, really around that time, this became one of the most important, sort of the holy grail of databases that everybody was racing. Every major vendor, from IBM to Oracle to Microsoft to SAP, they were racing to come up with this a unified structure. How do I create this HTAP, hybrid transactional and analytical engine? And that's the sort of the focus of my research back then, and the focus of kind of looking at that for this course and in the previous offering of this course. And again, what the problem is, or what that conflict is, we talked about this again in the read layout. So we have records are stored contiguously. They are not compressed. If I want a change, I go do the change in place. For the columnar, instead, the column values are stored contiguously, and allows me to do compression, allows me to really do well read-only because it's compressed. If I were to change a particular record, that means I have to change everything. I have to break the compression, and I have to break the sizing, and things needs to be moved around. So it becomes prohibitively very expensive to do any kind of in-place update or changes. But it's going to potentially get you 100x improvement on the performance of read analytics. So that's the initial conflict, or that's the initial sort of the dilemma that it's faced when you try to combine or unify this at the storage. So we have to unify this at the storage. We have to unify this at the buffer pool. We have to unify this at the concurrency, at the transaction, at many different layers, that unification needs to happen. But this is just, for now, we're just going to focus on the storage. And then subsequent milestone, we're going to look at other aspects of this, the facet of this problem as well too. So, and then what we find is that in this operational data store, and what operational data store is defined as, it's for not only for day-to-day tasks, but I want to be able to do my reporting. I have this gap. I have this gap between row-wise, and I have this gap between column-wise. And what the solution that we worked over the years, so over that 4 years span of, over that 4 year span, is develop this lineage-based storage architecture that allows us to operate on the native columnar storage and without the constant contention that caused by frequent updates. So how do I do column store, and how do I do updates very quickly or very efficiently? And the key idea is that first, I'm going to avoid in-place update. I want to just do append only. And what's beneficial about the append only is that I am not, once a data becomes finalized, appended, no longer that data is going to be changed. So whoever reading is that data have much more guarantee that what they're reading is not changing all of a sudden on them. So they don't have to, there's not much of need of locking. And sort of when you want to read something, tell everybody else, hold on, let me read it before you come in. And so that's an important element. But the other element is that, okay, if I'm doing a read only, if I'm doing an append only, then eventually all my data, my original data that I've written, is going to be overwritten at some point. And now if I want to read something, is that I have to go to the original data, and then I have to go to the updates, and maintaining these deltas becomes really cumbersome. It becomes difficult. Sure, at the time of write, it was really easy. So append only is a compromise, so I can really get fast write throughput. I can really do updates very quickly by append. But then over long term, if I'm continuously now want to do analysis, I have my base data and I have all these deltas, or I have all these tails that the terminology that we're going to use. But then I have to consolidate the delta with the base to form what the record looks like right now, after it has gone through a set of updates. So that now becomes a problem so the append only helped the problem of writes, but then this append only create a side effect of delta. So now sort of a large analytical type of query needs to consolidate the original data with the delta, and that becomes costly. So now you say, okay, well, it becomes costly. Of course, that's one thing comes to mind, pretty straightforward, is that, well, why don't I consolidate? So I consolidate my delta with my original data, and then just have a new updated base data. And that's what the word base comes. So I don't have to, when I'm doing my, so now for future queries after the reconciliation step, I no longer need to keep looking at the delta. I no longer need to look at the tail. So, but now the question is, how do you do this consolidation in a completely free, contention-free way? Because if I saved on locking and I saved on contention at the time of write, append only, update, but then I have to do this consolidation, and this consolidation just brings the whole system to the halt while I do the consolidation, then I may be in a worse situation that I start off. Why? Because if I paid extra for every update during the normal operation, at a steady state, my performance was not so great, for example. But if I kind of delay that and just do it sporadically or periodically, then all of a sudden the system is operating at perhaps a really good pace, at a really fast rate, but then it has these so unpredictable time. All of a sudden, all the system goes down, customer cannot access the website, it becomes chaotic. So it's actually worse, Because when you talk about systems and databases, or in general, sort of the backbone of the enterprise, the service level agreement is important, is that you want to make sure that you provide steady service level agreement. Everything can be done in less than a second. You don't want to be in a situation where you usually can do everything a tenth of a second, but then there is this unpredictable period of the time that anything you want to do is going to take 30 seconds. I mean, that would be kind of a disastrous for any kind of operation. Is that, for example, if you go on Amazon, sometimes it takes you 10 seconds to complete your shopping cart, and sometimes it takes you 10 minutes. Probably we're not going to go back to use Amazon probably very quickly after, if that happens 1 or 2 times. So the steady state of being able to add, maintaining that steady state without this fluctuation, it's an important design. So again, so that becomes at the core of this. So all of the decision, everything that we do, it culminates at this point of I can create delta efficiently, but I can create tail efficiently. But the most important thing is I can do this reconciliation very efficiently and almost like in the background without interfering with anything that is happening in the foreground. I mean, anything that any kind of a foreground transaction. So do it completely in the background, and that becomes sort of the essence of this of ELK-STOR and this whole line of work. And that's what we kind of, by the end of this quarter, we kind of get that intuition and how that all these different pieces finally come together to allow us to have this design that achieve these goals. Of course, there's a lot. This is sort of a first step. We can improve this in so many different directions, and I think that would be even a more important goal as you kind of learn throughout this course. You think about, how am I going to do this better? What are the shortcomings, or what are the opportunities that I can even do this better? And I think that's really important, that we all have that mindset to start kind of tapping into that our own creativity. So again, that's something that is really important for me, and I really want all of you to take the time to explore that yourself as well. Okay, any questions so far? A little bit we stayed on the high level to kind of set the stage. Now let's go a little bit more technical. So one thing is that let's kind of maybe at a high level. We have set of base pages, and these base pages, and again, as the question I believe Jim was asking earlier today, a base pages is a more a conceptual thing. Internally, a single base page consists of a bunch of pages, one for every column. So perhaps a single page here, if I have 4 columns, we can say it corresponds to 4 pages, one for each column at a sort of at a simple level. Now, when a record first initially gets inserted with its read, a read is allocated for that record. So this read becomes the anchor for this record, we can think of it in this context, at least becomes a logical ID for this record, and it never changes. So once I insert a record, that record gets a read, and that becomes a stable ID, a stable logical identifier for that record forever. And I mean, I could also make the record, the position of that record to be physical, and I kind of figured out that inside that integer, part of that, it would be the page ID, part of it would be the slot ID, and I could make that physical. And if I can also say, well, all the 4 pages for this record are identical, every column's of fixed size. I could make all kind of assumption and try to make that that base read, not just logical, but also physical. But I could just also make it logical and then use a page directory to translate that logical into a physical. I'll let you all kind of think about that on your own. So But when the record initially is inserted, they get a read, they get assigned to a base page. Now, later on, if this record gets updated, its update is added to the tail pages, to its corresponding tail page. So a set of base pages will have their update directed to a tail page. And once that tail page is full, then we'll create another tail page. So a set of base pages will correspond to a set of tail pages. So if I have another set of base pages down here, they will correspond to their own tail pages. So essentially, I'm partitioning my read space. I'm partitioning my records into these logical groups, maybe called page range, that for a page range, which consists of set of base pages, any update in those pages will go to a tail page. And if that tail page is full, well, I'll just have to create a new tail page and link back to that previous page. So that's kind of a very basic design. Now, another interesting thing comes is that what do I put in my indexes? Because I said I have these logical, once a record is established, it gets this stable read, and this has to be stable. Now, whether make it physical, logical, doesn't matter. It has to be a stable read. And the indexes will maintain they'll just maintain, or they point to this stable read. And so there must be a mapping layer that when I get this stable read, I could come here and potentially have a physical pointer to where the read is in the base page. But more importantly, from this lineage mapping, from this translation layer, I would also, or this is essentially an indirection layer, and there's nothing more but just an indirection, same as the indirection that we talk about in the page directory of the slot ID. I will have an indirection that points to the latest version of the record in the tail page. So I have a stable read. When a record is created, it's added to the base page, stable read gets created. That stable read is placed into the index. So from the index, when I follow that stable read, this indirection layer could point me to the physical location of that record. It also gives me a pointer to the latest version of the record. Or if and at the very least, this indirection will point me, and let me do that one step at a time. So we will kind of eliminate one of these. We're just going to have one layer here in this indirection. And so this indirection layer, it allows me to go from a logical read to a physical read. And it could give me a physical read to the base page, but it also could give me a physical read to a tail page. So that's why one is so the indirection has is a logical. This blue one is a physical read to where the location is in the base page, and the red one is a physical read where the record is in the tail page, at least in the conceptual. There are more simplification that we can do here. But that's a very high level design. Insertion goes to base pages, update goes to the tail pages, base page gets a read, tail record also gets a read, everything is pages, everything has read. At the lower level of the database, we have pages and reads. That's it. This concept of base page or tail page is a sort of conceptualization that are on top. But from the low level of the database, we have set of pages and we have a bunch of reads that are span across those pages. LID is the logical ID, LID is the logical read. So logical read versus the typical read, which tend to be more physical. So which typically is physical. You could have page ID and slot ID, and the page ID could be a physical reference. So that's your typical read. But here is the logical read, because in order for me, for example, to get the latest version of the record, so let's say the John has a logical read of 5. And this logical read of 5 initially was pointing to a base page here, but then later was updated, and this is the latest version of the record. So initially it had the read of 5, but in the tail record right now has a read of 175. So when I'm looking up the information from John, I look up the index. I know the latest version of it is in the physical read of 175, although the initial version of it was 5, and that's what is recorded in the index. So every time I add an update to that record, that means I assign a new tail read to it, I don't actually need to go ahead and change the indexes to say, okay, this is the new read of the record. The indexes always point to the initial read, which was 5. And from this indirection layer, given that the initial read of the record was 5, what is the latest read of the record right now? What is the latest version of the record? So this is done at this level of indirection, as opposed to now tell everybody John is no longer 5, it's 175, and that's fine, but now I have to go change every single index. Anywhere that was kind of maintaining that John is 0.25, I now have to go and update all of them to make it 175, because I have an update for it, and the update is now in this location. So that logical ID, it becomes stable, it never changes. And in order to find what's the latest version of it, I go to this indirection mapping. I go to this mapping, and this mapping converts a lid to a read. And so the lid is the initial inserted read, and the current physical read is the last version of the record that was added as a tail page. So that's the differentiation between lid and read. Any question? There's other important thing here as well, is that within each page, some lineage information is tracked. And this lineage information, which gives the name of lineage-based storage architecture, and later on we'll come to the importance of this lineage. And this plays a crucial role when it comes to reconciliation and other factors. We're going to go to more and more detail. So everything that I said, we're going to go in more depth. So kind of just figure of what I've just said. So when initially I create a read here, any update to that read, it will be append only to its corresponding tail pages. And reads are always monotonically increasing. Or you could make it decreasing. That's kind of, it's up to you, as long as they go in one direction. And the reason for that is that the first update could be read of 7, the next update is read of 13, and the latest update also points back to the previous one. I think it's enough to keep it. Some of the details come later. Every choice that we talk about, there is a justification for it, but we kind of need to learn more about it before we can explain those justifications. Now, eventually, as I said, I have my base pages, I maintain my delta, new changes in tail pages, but now if I'm doing analytics, I have to consolidate potentially both of these, because some of the fields may have never been updated, so I need to get them from the base pages. Some of the record has been updated, some of the field has been updated multiple times, and some of the records have been updated several times. So I need to keep consolidate my tail and base. So although with the concept of the tail page, I can efficiently handle the writes, I can efficiently handle the transaction, but my analytics begin at some point to slow down because of maintaining these deltas. So then we have this process of consolidation, which is the merge, focus of milestone 2, one of the focus of the milestone 2. And so periodically, we take the base pages with their corresponding tail pages, and we create a new consolidated data. And now once we have this consolidated data, the latest version of the record will all be here. I can get the latest version of the record from here, and I don't need to keep looking back to the tail pages. So that will speed up my analytics and simplifies my analytical type of quiz. So that's the second assignment, second milestone. So now, kind of, any question on that? Actually, before.
Yeah,
Yes.
Professor, I have a question. So the record on the base page, is that one pointing to the first update or the last update?
Which one here?
Yeah, on the base page. After you append a update, is that pointing to the last update or the very first update?
So the base page, it's a single record. The base page is a single slot that never changes. This base, once a record gets a base read, or even calling it a lid here, once it gets a base read of 5, it will always be 5. That will never change. That will never change. Its tail record will get changed. So for example, every time I first update, maybe the tail record is read 75. The second update, the tail read is 98, and so forth. Every update creates a new tail record, that read gets changed. And the latest read that is in the tail record can be, we can find it from the indirection. So the indirection is kind of, you can think of it as a simple hash table. I give you a lid or an anchored read. I give you a lid, and then you give me the latest tail page or tail read for that record. Just a simple hash table. I give you a stable lid, I give you a lid, you give me a read.
So Professor, so do we have multiple reads on the tail pages for one single base record, or do we have just one read on the tail pages for one base record?
No, so since every update is going to be append only to the tail page, every time you add a record, you get a read. Every record that is added, doesn't matter, is added to the base page or is added to, because read is that physical or either, if you can think of that physical, the logical identifier. There's that spot on the page. Every time a new spot allocated and is assigned, a new read is generated. So for every single update that I do to that record, for every one of them, a read J is allocated. Then a new record is added. So that I keep getting more and more reads. So that if I have 100 updates, I will have 100 tail records, and I will have 100 tail reads as well too. But it's always going to have that one stable read.
So the LID will never change the lid for a record?
Yes, exactly. It will never change.
Professor, so one last question.
Sure.
So the record on the base page, say you inserted 100 updates. So the record on the base page, is that pointing to the first update or the update number 100?
It will point to in that indirection mapping, this indirection points to the latest version. So it points to the latest version of the read. So if this is 100 update, the read 5, which was our stable read, if I give my read 5 to this indirection mapping, think of it maybe as a hash table, give me the lid or the stable read is 5, give me the latest tail, it gives me the 100th record. And the 100 could have the read of 750, for example, maybe just any number.
Okay.
My 100th update could be the 750 update that was kind of seen, because there's other records, there's other updates that are happening that goes to these tail pages. So it's not just one record that is being updated.
Okay, thank you, Professor.
So maybe we can spend another 2 minutes if any other question, because we kind of will again dedicate the entire next session to this. And for those of you who want to kind of see the rest of this, all the recording from last year, I have gone over all of these as well too. We're going to go over it together, but if you kind of want to sort of be one step ahead and sort of what's going to come next, you can also look at last year recording as well too.
So I think I understand like how records are appended, but could you like very quickly describe how the read-only would go? I guess like at a high level.
What do you mean by the read-only? You mean here?
Yeah, like you're saying like for analytics, like can you just walk me through that real quick?
Sure. So when I'm doing an update, I read my base page, or I read the latest version of the record, and then whatever changes I need to make, then I add a tail record. Is that does that part make sense?
Yeah, that part makes sense.
Okay, so now I'm doing an analytics. I know for the other thing is that since I'm doing append only, these pages, these base pages, once they've written, once I insert to a base page and I fully insert it, this page becomes read only. This page never gets changed because any update to this page, it goes to an append only to the tail. So this is essentially a read only page. This page will never get dirty in the buffer pool either. There's never need for me to rewrite that page back to disk. So that's why this is read only. These tail pages are append only. Once a tail record read RJ is written, I will never go and change that. The only thing that happens, I add new record at the end. So once something is written, it will never be changed. And that's crucial in the entire design. Once something is written, will never be changed. That space will never be changed. We're never going to modify it. If I need to make a change, I'll make a new copy and I append the changes. So the original will never change. So that's why these base pages are read-only. These tail pages are append-only. In fact, the base pages starts as append-only because once I allocate a new base page, I start inserting my new records. Once that base page is full, I need to allocate a new page because I want to do insertion. Insertion goes to base pages, update and deletion goes to tail pages. But once something is full, becomes read-only. Once the tail page also becomes full, also becomes read-only. So that's the read-only part. Now for the analytics, well, we talked about the update, but for the analytics, we could just read the base pages, but they're not going to get the latest version. So that's why they need to read the base pages, and they also need to read the tail pages to make sure they have the latest version of every single record, if that's something they need. And maybe the analytics might be sufficient that they can be slightly behind. And maybe the data in the base pages for them is sufficient. But if they need the absolute latest data, then they also need to look at the tail pages. And we're going to talk about that in more detail again next time too. Yes, please go ahead.
I guess going off that, so like if you're querying, are you querying off the base pages or are you following the indirection down to the most latest update? Or are you usually just pulling information when you're querying from the base page?
So that's a very good question. So if I am doing an index lookup, I'll look at for Alice. And so from the Alice, the index tells me the stable lid is 5. And I know my stable, and I know the 5 is the anchor, the initial lid, the initial read that was assigned. But if I need the latest version of it, I come to the indirection. I say, well, give me the latest version for record 5. It gives me the read K. So from there, I can come to the tail page, to the last tail page that maintains the latest update for this record. And so if every columns of that record was updated, well, they're all going to be in this record. So I can just read the latest version. But it might be possible that only one of the column of the record was updated. So the tail page will only maintain or will only have the only columns that was updated. The other 3 columns that was never updated will remain in base pages only. So I need to read maybe if the 3rd column was the one that was updated, the 3rd column of that record, I need to read from the tail page because that gives me the latest value. But the 1, 2, 3, 1, 2, and 4, let's say there were only 4 columns, the 1, 2, and 4 columns, their latest version still in the base page because they were never updated. So then I may also have to read the base pages depending on what needs to be returned to the user. Does that answer your question?
Yeah, I guess, sorry, I think I have a little bit of a lag. Is that a choice as the programmer to decide how is it our choice as a programmer to decide how current of information we provide back to the user when they do their queries?
Yeah, so that's a good question. No, so what we need to do is we provide isolation semantics. We provide a sort of guarantee. So the user, so usually what the database provides, I can give you the latest version. I can give you a version, a committed version, some version that was correct, committed at some point in time. Or I could give you a version that, well, is currently being changed by someone. That change has already been applied, but it's possible that the transaction is changing it, later decide, well, they're going to drop it on the board, so they're going to undo their changes. But I can give you this data that could potentially be invalidated. And well, if you read it, and if it's invalidated, well, it's nothing can be done. So that was the choice of the user. So oftentimes this is the user can choose, at least traditional. The traditional databases gave the options of what isolation semantics, what they call it, what level of consistency the user wishes to see. They want to see always the latest version, or they're okay if they see a slightly outdated version. Some of the newer systems, especially with key value store and also around the big data hype, they fundamentally said it is possible that the version you're reading is not the latest version. And that's the best we can do. And we can't even guarantee how far we are. You may be kind of reading it, you may be 5 minutes behind. There may be many updates in the last 5 minutes, and well, if you do a read, you're not going to see that. And what was their motivation? Justification, which does make sense. It's of course not a generic solution, is that, well, if somebody posts the image on Facebook, and especially that person happened to be famous, and everybody started liking it, and as a user, you kind of come and look at that post, and you see, oh, it has 75,000 likes. Now, if in fact it's 75,200 likes, and you didn't see the last 200 likes, well, it's not the end of the world. I think we can all live if we don't see every single likes that was added to a picture, and if there's a lag there. So they kind of notice is a lot of in the social media data and in a lot of web data, it's often not necessary that you see absolute latest. And so we say fundamentally the system not even gonna even try to guarantee you to give you the latest version of the record, the latest version of the data. And that fundamentally allowed them to simplify and help them to scale the system by losing that ability, versus the traditional databases, sort of well, they call it the SQL versus the NoSQL. You probably all of you did the research in your pre-milestone as well too. The NoSQL, one thing that they did, they relaxed the capability that they were provided to the user to allow them to scale. The traditional system says, no, it is important to allow the user to see always the latest, and otherwise it becomes a complete mess for the developer of the application, because it's so hard not to reason about these data. And I think the Twitter CTO said something interesting is that, and they call this kind of, eventually you get the right version of the data, call it the eventual consistency. And I believe it was the CTO of Twitter says, I guess after years of kind of practicing, experimenting with these eventual consistency or NoSQL databases, made the statement, all the eventual consistency will eventually be inconsistent. Eventual consistency eventually becomes inconsistent because it just becomes so difficult. Already building an application is difficult when you know that what you're given is correct. But now if you say, well, what you have may not be the latest version, may not be correct, then you put that burden on the developer to make sure the correct action is still taking place so that they don't sell a book that they don't have in stock just because they didn't get the update on the inventory in time. So they now add to have a lot of corner cases. So it makes the task that the database initially was supposed to do, the database says, I'm not going to do it, but I can do things faster now because I'm not going to give you the same guarantee. Now the application says, great, now I can do things faster because the database can do it faster. But now I have to deal with all these different corner cases, which cleanly the database used to handle. Now it goes on to the choice of the developer, how it's going to handle. They may not even be aware of all the possible corner cases. So the application becomes more and more challenging and difficult to cope with. And then this kind of led to the new SQL. The new SQL was essentially reversing what the NoSQL has said and going back to SQL, but with the hype name of new SQL. But more or less, they kind of went back to the original design that these guarantees are important because it simplifies the development of applications. That was a long answer, but I wanted to kind of give you a little bit of context on where all this is coming from.
Oh, that was great. Thank you.
You're welcome. Any other question?
I've got a quick one. I know we have a couple pages that we're maintaining for each base page that isn't exposed to people querying the data, and that's the indirection page and the schema page, right?
Mm-hmm.
And those are updated, so those aren't read-only. Those get updated based on how the tail pages are appended.
Yes.
Correct. Okay.
Yes.
And then
so essentially, since we're at that point, this indirection column, which is kind of showing as a separate structure, as you said, is later going to be just a column of the table. So there will be a column of the table that if I read that column, the value of that column gives me the latest version in the tail page. And as you said, that's actually in contrary to what we say here, that the base pages are read-only. These columns are not just read-only, and they're not just append-only. They're actually do in-place update in it, because we do an in-place update to point to the latest version of the record. But the interesting part is that since these are fixed pointer size, they're 8 bytes, then we can do compare and swap. We can do atomic operation as opposed to holding log. Given the special structure of these, it allows us to do latch-free or log-free updates. And so and we kind of touched upon that in the R hash as well too. So that's what makes that column, both of those columns, special just because of its type of the data and as a structure. So, and that's where the gap is. So that's how that gap is closed. And there's a few more other things around it too, which hopefully by the end of these slides, I think we will have touched upon it.
So for our implementation for milestone 1, as we're trying to incorporate those, are we just using integer? Is that okay to assume that it's the same size, or do we need to, do we have?
You can assume everything is integer. You can assume all your data types are integer.
Okay. Right.
Everything fixed size, everything integer. For your first assignment, also there's only a single user, single thread. So if you have a serial execution single thread, there's no lock involved because only one thing is happening at a time anyway. So for first assignment, things are really simple from that perspective. For the second assignment, we will have a background merge. but that's the way it's designed has minimal interference with transactions anyway, almost none. And for the third assignment, then we talk about multiple transaction. Now we're really going to deal with locks and locking the page. And we don't have to do a latch query. We can just, for example, for that page and for a particular page that you need to change for indirection, we could just lock that page. So that's fine for our implementation. But then we need to worry about those race conditions. But that's really comes into the third milestone.
I guess I have one more question if no one else is going to chime in. When we talk about a page range, say a page range is responsible for whatever, 100 records, we can just keep appending tail pages as long as those specific records are updated. That page range doesn't restrict the amount of tail pages we could potentially spawn at this point, right?
Yeah, so so the page range is only limits the number of base pages in a sense, or the number of base reads. But a single record could get updated 10 million times. And to hold 10 million updates, you may need 10,000 pages, and so be it.
Right.
So that's a unbounded list of pages, list of tail pages.
Okay, thank you.
I have a quick one.
Sure.
With deletion, there mentioned that there is a special nil value that we could use. Like for integer values, what values could we use to be as null?
So for deletion, so again, that becomes a little bit more interesting there too, is that you don't necessarily need to mark the actual column value as deleted. For example, you could have like a flag, just making an example. You could have a flag in your latest read. Have one bit as a flag. If that flag is set, then that record needs to be deleted. So that indicator doesn't have to actually be on the value itself. You could have that flag somewhere else. You could think about what are other ways of doing it. But for example, one way is that the base so if, for example, if a base version was never deleted, it was never updated, a base record 5 was never updated, in its indirection column, I could just put 0, for example. I could just put -1. And -1 means this record has never been updated and also has been deleted because it's -1. And so that's one way of doing it. But if that indirection is already set, meaning that record was updated already once, a tail record, a read, if you have 8 bytes, that's 64 bits. And you may not need 64 bits, all the 64 bits just for your read space, because you're not going to have that many reads anyway. So you could say, well, I'm going to have 63 bits for the actual value of the read, and one of the bits I am going to keep it for whether this is deleted or not. So if that bit is set, it could be any of those. It could be the last one or the first one. If that bit is set, that means that the record is deleted. So that could be another indication for something to be deleted. You can think of other ways of doing it. So that's different from going and changing, making a data value itself deleted, because there is difficult, because if it's integer, it could 0 is a valid value, -1 is a valid value. So you need, again, another special indicator symbol. So for example, what you could have, if you have if it's in your page, you have a directory, you know how we had the slot number, and the slot number was pointing, for example, to the physical position of the record. And we also had another directory that we had the bit map. The bits, if it was 0 or 1, it was tell us whether that record was deleted or not. So every page could have a bitmap and say whether a particular slot is deleted or not. If it's set to 0 or 1, it indicates that, again, you don't actually change the actual value of the field. You can think of creative secondary structure that helps you to mark that as deleted.
Thank you.
You're welcome. All right, so I guess have a wonderful day and a wonderful remainder of the week. Yes, go on, please.
So, do we need the schema encoding if the updates are cumulative?
Yes, because you still may not update every single record.
Okay. All right,
So
thank
the
you.
schema encoding tells you which record was updated.
Okay. Thank you.
You're very welcome. All right, everybody, have a wonderful day and see you guys on Thursday.